You are listening to Audio SSLC, your audio medium for easy understanding and revision. To download a copy of this recording, please visit audiosslc.com. Chapter 13: Magnetic Effects of Electric Current. In the previous chapter on electricity, we learned about the heating effects of electric current. What could be the other effects of electric current? We know that an electric current carrying wire behaves like a magnet. Let us perform the following activity to reinforce it. In this activity, take a straight, thick copper wire and place it between the points X and Y in an electric circuit. Please refer to figure 13.1. The wire XY is kept perpendicular to the plane of the paper. Horizontally, place a small compass near to this copper wire and see the position of its needle. Pass the current through the circuit by inserting the key into the plug. Then observe the change in the position of the compass needle. We see that the needle is deflected. What does it mean? It means that the electric current through the copper wire has produced a magnetic effect. Thus, we can say that electricity and magnetism are linked to each other. Then what about the reverse possibility of an electric effect of moving magnets? In this chapter, we'll study magnetic fields and such electromagnetic effects. We shall also study about electromagnets and electric motors, which involve the magnetic effect of electric current, and electric generators, which involve the electric effect of moving magnets. Hans Christian Ørsted, 1777 to 1851. He was one of the leading scientists of the 19th century. He played a crucial role in understanding electromagnetism. In 1820, he accidentally discovered that a compass needle got deflected when an electric current was passed through a metallic wire placed nearby. Through this observation, Ørsted showed that electricity and magnetism were related phenomena. His research later created technologies such as the radio, television, and fiber optics. The unit of magnetic field strength is named the Ørsted in his honor. Let's learn about magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle is, in fact, a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end pointing towards north is called north-seeking or north pole. The other end that points towards south is called south-seeking or south pole. Through various activities, we have observed that like poles repel, while unlike poles of magnets attract each other. Let's look at the question. Why does a compass needle get deflected when brought near a bar magnet? In the next activity, fix a sheet of white paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron filings uniformly around the bar magnet. Please refer figure 13.2. A salt sprinkler may be used for this purpose. Now tap the board gently. What do you observe? The iron filings arrange themselves in a pattern as shown in figure 13.2. Why do the iron filings arrange in such a pattern? What does this pattern demonstrate? The magnet exerts its influence in the region surrounding it. Therefore, the iron filings experience a force. The force thus exerted makes iron filings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field. The lines along which the iron filings align themselves represent magnetic field lines. Are there other ways of obtaining magnetic field lines around a bar magnet? Yes, you can yourself draw the field lines of a bar magnet. In the next activity, you take a small compass and a bar magnet. Then place the magnet on a sheet of white paper that is fixed on a drawing board using some adhesive material. Then mark the boundary of the magnet. Next, place the compass near the north pole of the magnet. How does it behave? The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. Now move the needle to a new position such that its south pole occupies the position that was previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet as shown in figure 13.3. Now join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the above procedure and draw as many lines as you can. You'll get a pattern shown in figure 13.4. These lines represent the magnetic field around the magnet. These are known as magnetic field lines. Observe the deflection in the compass needle as you move it along a field line. The deflection increases as the needle is moved towards the poles. Magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, it is taken by convention that the field lines emerge from north pole and merge at the south pole. You please note the arrows that are marked on the field lines in figure 13.4. Inside the magnet, the direction of field lines is from its south pole to its north pole. Thus, the magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. The field is stronger, that is, the force acting on the pole of another magnet placed is greater where the field lines are crowded. Please see figure 13.4. No two field lines are found to cross each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. Next, let's come to magnetic field due to a current carrying conductor. In activity 13.1, we've seen that an electric current through a metallic conductor produces a magnetic field around it. In order to find the direction of the field produced, let us repeat the activity in the following way. Take a long straight copper wire, 2 or 3 cells of 1.5 volts each, and a plug key. Connect all of them in series as shown in figure 13.5a. Place the straight wire parallel to and over a compass needle. Plug the key in the circuit. Observe the direction of deflection of the north pole of the needle. If the current flows from north to south as shown in figure 13.5a, the north pole of the compass needle would move towards the east. Replace the cell connections in the circuit as shown in figure 13.5b. This would result in a change of the direction of current through the copper wire, that is, from south to north. Observe the change in the direction of deflection of the needle. You'll see that now the needle moves in opposite direction, that is, towards the west. Refer figure 13.5b. It means that the direction of magnetic field produced by the electric current is also reversed. Next, let's come to magnetic field due to a current through a straight conductor. What determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of the magnetic field around a straight conductor carrying current. In the activity, you take a battery of 12 volts, a variable resistance or a rheostat, an ammeter 0 to 5 amps, a plug key, connecting wires, and a long straight thick copper wire. Then insert the thick wire through the center, normal to the plane of a rectangular cardboard. Take care that the cardboard is fixed and does not slide up or down. Connect the copper wire vertically between the points X and Y as shown in figure 13.6a in series with the battery, a plug and key. Next, sprinkle some iron filings uniformly on the cardboard. You may use a salt sprinkler for this purpose. Then keep the variable of the rheostat at a fixed position and note the current through the ammeter. Next, close the key so that a current flows through the wire. Ensure that the copper wire placed between the points X and Y remains vertically straight. Then gently tap the cardboard a few times. Observe the pattern of the iron filings. You'd find that the iron filings align themselves, showing a pattern of concentric circles around the copper wire. Please refer figure 13.6. Now, what do these concentric circles represent? They represent the magnetic field lines. How can the direction of the magnetic field be found? Place a compass at a point, say P, over a circle. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines that are produced by the electric current through the straight wire at point P. Show the direction by an arrow. Now, does the direction of magnetic field lines get reversed if the direction of the current through the straight copper wire is reversed? Check it. What happens to the deflection of the compass needle placed at a given point if the current in the copper wire is changed? To see this, vary the current in the wire. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. What happens to the deflection of the needle if the compass is moved away from the copper wire, but the current through the wire remains the same? To see this, now place the compass at a farther point from the conducting wire, say at point Q. What change do you observe? We see that the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. From figure 13.6, it can be noticed that the concentric circles representing the magnetic field around a current-carrying straight wire become larger and larger as we move away from it. Coming to the right-hand thumb rule, a convenient way of finding the direction of magnetic field associated with a current-carrying conductor is given in figure 13.7. Imagine that you're holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of the current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field as shown in figure 13.7. This is known as the right-hand thumb rule. In example 13.1, a current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and at a point directly above it? In the solution, the current is in the east-west direction. Applying the right-hand thumb rule, we get that the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire. When viewed from the east end, perpendicular to the wire when viewed from the east end, and anti-clockwise when viewed from the west end. Coming to the questions, number 1, draw magnetic field lines around a bar magnet. Number 2, list the properties of magnetic field lines. Number 3, why don't two magnetic field lines intersect each other? Next, let's learn about the magnetic field due to a current through a circular loop. We've so far observed the pattern of the magnetic field lines produced around a current-carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current-carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current-carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. Please refer figure 13.8. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. By applying the right-hand rule, it's easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. This rule is also called Maxwell's corkscrew rule. If we consider ourselves driving a corkscrew in the direction of the current, then the direction of the rotation of corkscrew is the direction of the magnetic field. We know that the magnetic field produced by a current-carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up. In the next activity, take a rectangular cardboard having 2 holes. Insert a circular coil having large number of turns through them, normal to the plane of the cardboard. Next, connect the ends of the coil in series with a battery, a key and a rheostat as shown in figure 13.9. Then sprinkle iron filings uniformly on the cardboard. Next, plug the key. Then tap the cardboard gently a few times. Note the pattern of the iron filings that emerges on the cardboard. Let's move on to learning the magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The pattern of the magnetic field lines around a current-carrying solenoid is as shown in figure 13.10. Compare the pattern of the field with the magnetic field around a bar magnet. Please look at figure 13.4. Do they look similar? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. You can refer to figure 13.11. The magnet so formed is called an electromagnet. Let's get down to questions. Number 1. Consider a circular loop of wire lying in the plane of the table. Let the current pass through the loop clockwise. Apply the right-hand rule to find out the direction of the magnetic field inside and outside the loop. Number 2. The magnetic field in a given region is uniform. Draw a diagram to represent it. Number 3. Choose the correct option. The magnetic field inside a long straight solenoid carrying current is A. 0, B. Decreases as we move towards its end, C. Increases as we move towards its end, or D. Is the same at all points. Let's move on to learning the force on a current-carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet that is placed in the vicinity of the conductor. French scientist André-Marie Ampère, 1775 to 1836, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. The force due to a magnetic field acting on a current-carrying conductor can be demonstrated through the following said activity. Take a small aluminium rod AB of about 5 cm. Using 2 connecting wires, suspend it horizontally from a stand. Please refer to figure 13.12. Then place a strong horseshoe magnet in such a way that the rod lies between the poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod from end B to end A. What do you observe? It is observed that the rod is displaced towards the left. You'll notice that the rod gets displaced. Now reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. Now, why does the rod get displaced? The displacement of the rod in the above activity suggests that a force is exerted on the current-carrying aluminum rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current-carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest, or the magnitude of the force is the highest, when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor. In activity 13.7, we considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. The three directions can be illustrated through a simple rule called Fleming's left-hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular to each other. Please refer figure 13.13. If the first finger points in the direction of magnetic field and the second finger in the direction of the current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current-carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones, and measuring instruments. In the next few sections, we shall study about electric motors and generators. Example 13.2. An electron enters a magnetic field at right angles to it. As shown in figure 13.14, the direction of force acting on the electron will be A to the right, B to the left, C out of the page, D into the page. The solution. Here the answer is option D. The direction of force is perpendicular to the direction of magnetic field and current as given by Fleming's left-hand rule. Recall that the direction of current is taken opposite to the direction of motion of electrons. The force is therefore directed into the page. Moving to the questions. Number 1. Which of the following property of a proton can change while it moves freely in a magnetic field? Here there may be more than one correct answer. The options are A. Mass, B. Speed, C. Velocity, or D. Momentum. Question 2. In activity 13.7, how do we think the displacement of rod AB will be affected if number 1. The current in rod AB is increased, number 2. A stronger horseshoe magnet is used, and number 3. Length of the rod AB is increased. Question 3. A positively charged particle, that is alpha particle, projected towards west is deflected towards north by a magnetic field. The direction of magnetic field is A. Towards south, B. Towards east, C. Downward, or D. Upward. Next, let's learn about electric motor. An electric motor is a rotating device that converts electrical energy into mechanical energy. Electric motor is used as an important component in electric fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Do you know how an electric motor works? An electric motor, as shown in figure 13.15, consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field such that the arm AB and CD are perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves P and Q of a split ring. The inner sides of these halves are insulated and attached to an axle. The external conducting edges of P and Q touch two conducting stationary brushes X and Y respectively, as shown in figure 13.15. Current in the coil ABCD enters from the source battery through conducting brush X and flows back to the battery through brush Y. Notice that the current in arm AB of the coil flows from A to B. In the arm CD, it flows from C to D, that is opposite to the direction of current through arm AB. On applying Fleming's left-hand rule for the direction of force on a current-carrying conductor in a magnetic field, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. Thus, the coil and the axle O, mounted free to turn about an axis, rotate anticlockwise. At half rotation, Q makes contact with the brush X and P with the brush Y. Therefore, the current in the coil gets reversed and flows along the path DCBA. A device that reverses the direction of the flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. The reversal of current also reverses the direction of force acting on the two arms, AB and CD. Thus, the arm AB of the coil that was earlier pushed down is now pushed up, and the arm CD, previously pushed up, is now pushed down. Therefore, the coil and the axle rotate half a turn more in the same direction. The reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil and to the axle.
You are listening to Audio SSLC, your audio medium for easy understanding and revision.
To download a copy of this recording, please visit audiosslc.com. The commercial motors use, number 1, an electromagnet in place of permanent magnet. Number 2, large number of turns of the conducting wire in the current-carrying coil. And number 3, the soft iron core on which the coil is wound plus the coils is called an armature. This enhances the power of the motor. Coming to the questions part, number 1, state Fleming's left-hand rule. Number 2, what is the principle of an electric motor? Number 3, what is the role of the split ring in an electric motor? Next, let's learn about electromagnetic induction. We've studied that when a current-carrying conductor is placed in a magnetic field such that the direction of current is perpendicular to the magnetic field, it experiences a force. This force causes the conductor to move. Now, let's imagine a situation in which a conductor is moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. What will happen? This was first studied by English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. To observe this effect, let's perform the following said activity. Take a coil of wire AB having a large number of turns. Then connect the ends of the coil to a galvanometer as shown in figure 13.16. Take a strong bar magnet and move its north pole towards the end B of the coil. Do you find any change in the galvanometer needle? There is no momentary deflection in the needle of the galvanometer, say to the right. This indicates the presence of a current in the coil AB. The deflection becomes zero the moment the motion of the magnet stops. Now withdraw the north pole of the magnet away from the coil. Now the galvanometer is deflected towards the left, showing that the current is now set up in the direction opposite to the first. Next, place the magnet stationary at a point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects towards the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves towards the left when the coil is moved away. When the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to zero. So what do you conclude from this activity? A galvanometer is an instrument that can detect the presence of a current in a circuit. The pointer remains at zero, that is the center of the scale, for zero current flowing through it. It can deflect either to the left or to the right of the zero mark, depending on the direction of the current. You can also check that if you had moved south pole of the magnet towards the end B of the coil, the deflections in the galvanometer would just be opposite to the previous case. When the coil and the magnet are both stationary, there is no deflection in the galvanometer. It is thus clear from this activity that motion of a magnet with respect to the coil produces an induced potential difference, which sets up an induced electric current in the circuit. Michael Faraday, 1791 to 1867. He was an experimental physicist. He had no formal education. He worked in a bookbinding shop during his early years. He used to read books that came for binding. This way, Faraday developed his interest in science. He got an opportunity to listen to some public lectures by Humphrey Davy of Royal Institute. He made careful notes of Davy's lectures and sent them to Davy. Soon he was made an assistant in Davy's laboratory at the Royal Institute. Faraday made several path-breaking discoveries that include electromagnetic induction and the laws of electrolysis. Several universities conferred on him the honorary degrees, but he turned down such honors. Faraday loved his science work more than any honor. Let us now perform a variation of activity 13.8 in which the moving magnet is replaced by a current-carrying coil and the current in the coil can be varied. So, in the activity, take two different coils of copper wire having large number of turns, say 50 and 100 turns respectively. Insert them over a non-conducting cylindrical roll as shown in figure 13.17. You may use a thick paper roll for this purpose. Connect the coil 1 having larger number of turns in series with a battery and a plug key. Also connect the other coil 2 with a galvanometer as shown. Plug in the key. Observe the galvanometer. Is there a deflection in its needle? You'll observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to zero, indicating a momentary current in coil 2. Disconnect coil 1 from the battery. You'll observe that the needle momentarily moves, but to the opposite side. It means that now the current flows in the opposite direction in coil 2. So in this activity, we observe that as soon as the current in coil 1 reaches either a steady value or zero, the galvanometer in coil 2 shows no deflection. From these observations, we conclude that a potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing, that is starting or stopping. Coil 1 is called the primary coil and coil 2 is called the secondary coil. As the current in the first coil changes, the magnetic field associated with it also changes. Thus, the magnetic field lines around the secondary coil also change. Hence, the change in the magnetic field lines associated with the secondary coil is the cause of induced electric current in it. This process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. In practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. It is convenient in most situations to move the coil in a magnetic field. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. In this situation, we can use a simple rule to know the direction of the induced current. Stretch the thumb, forefinger and middle finger of the right hand so that they are perpendicular to each other as shown in figure 13.18. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of the motion of the conductor, Then the middle finger will show the direction of the induced current. This simple rule is called Fleming's right-hand rule. Moving to the question, number 1. Explain the different ways to induce current in a coil. Let's move on to electric generator. Based on the phenomenon of electromagnetic induction, the experiments studied above generate induced current, which is usually very small. This principle is also employed to produce large currents for use in homes and industry. In an electric generator, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. An electric generator, as shown in figure 13.19, consists of a rotating rectangular coil ABCD placed between the two poles of a permanent magnet. The two ends of this coil are connected to the two rings R1 and R2. The inner side of these rings are made insulated. The two conducting stationary brushes, that is B1 and B2, are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to the galvanometer to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated, such that the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. Let's say the coil ABCD is rotated clockwise in the arrangement as shown in figure 13.19. By applying Fleming's right-hand rule, the induced currents are set up in these arms along the directions AB and CD. Thus, an induced current flows in the direction ABCD. If there are a larger number of turns in the coil, the current generated in each turn adds up to give a large current through the coil. This means that the current in the external circuit flows from B2 to B1. After half a rotation, the arm CD starts moving up and AB moving down. As a result, the directions of the induced currents in both the arms change, giving rise to the net induced current in the direction DCBA. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms changes. Such a current, which changes direction after equal intervals of time, is called an alternating current, abbreviated as AC. This device is called an AC generator. To get a direct current or DC, which does not change its direction with time, a split ring type commutator must be used. With this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. We've seen the working of a split ring commutator in the case of an electric motor. See figure 13.15. Thus, a unidirectional current is produced. The generator is thus called a DC generator. The difference between the direct and alternating currents is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Most power stations constructed these days produce AC. In India, the AC changes direction after every 1/100th of a second. That is, the frequency of AC is 50 Hz. An important advantage of AC over DC is that the electric power can be transmitted over long distances without much loss of energy. Coming to the questions, number 1. State the principles of an electric generator. Number 2. Name some sources of direct current. Number 3. Which sources produce alternating current? Number 4. Choose the correct option. A rectangular coil of copper wires is rotated in a magnetic field. The direction of the induced current changes once in each, and the options are A. 2 revolutions, B. 1 revolution, C. half revolution, or D. 1/4 revolution. Coming to domestic electric circuits, In our homes, we receive supply of electric power through a main supply, also called as the mains, either supported through overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called live wire or positive. Another wire with black insulation is called neutral wire or negative. In our country, the potential difference between the two is 220 volts. At the meter board in the house, these wires pass into an electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. These wires supply electricity to separate circuits within the house. Often, two separate circuits are used, one of 15 amp current rating for appliances with higher power ratings, such as geysers, air coolers, etc. The other circuit is of 5 amp current rating for bulbs, fans, etc. The earth wire, which has insulation of green color, is usually connected to a metal plate deep in the earth near the house. This is used as a safety measure, especially for those appliances that have a metallic body. For example, electric press, toaster, table fan, refrigerator, etc. The metallic body is connected to the earth wire, which provides a low resistance conducting path for the current. Thus, it ensures that any leakage of current to the metallic body of the appliance keeps its potential to that of the earth, and the user may not get a severe electric shock. Figure 13.20 gives a schematic diagram of one of the common domestic circuits. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has a separate switch to on or off the flow of current through it. In order that each appliance has equal potential difference, they are connected parallel to each other. Electric fuse is an important component of all domestic circuits. We've already studied the principle and working of a fuse in the previous chapter. See section 12.7. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Overloading can occur when the live wire and the neutral wire come into direct contact. This occurs when the insulation of wires is damaged or there is a fault in the appliance. In such a situation, the current in the circuit abruptly increases. This is called short circuiting. The use of an electric fuse prevents the electric circuit and the appliance from a possible damage by stopping the flow of unduly high electric current. The joule heating that takes place in the fuse melts it to break the electric circuit. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes overloading is caused by connecting too many appliances to a single socket. In the questions, number 1, name 2 safety measures commonly used in electric circuits and appliances. Number 2, an electric oven of 2 kilowatt power rating is operated in a domestic electric circuit that is 220 volts and that has a current rating of 5 amps. What result do you expect? Explain. Question 3. What precaution should be taken to avoid the overloading of domestic electric circuits? Let's come to what you have learned so far. Number 1. A compass needle is a small magnet. Its one end, which points towards north, is called a north pole, and the other end, which points towards south, is called a south pole. 2. A magnetic field exists in the region surrounding a magnet in which the force of the magnet can be detected. 3. Field lines are used to represent a magnetic field. A field line is the path along which a hypothetical free north pole would tend to move. The direction of the magnetic field at a point is given by the direction that a north pole placed at that point would take. Field lines are shown closer together where the magnetic field is greater. 4. A metallic wire carrying an electric current has associated with it a magnetic field. The field lines about the wire consist of a series of concentric circles whose direction is given by the right-hand rule. Number 5. The pattern of the magnetic field around a conductor due to an electric current flowing through it depends on the shape of the conductor. The magnetic field of a solenoid carrying a current is similar to that of a bar magnet. 6. An electromagnet consists of a core of soft iron wrapped around with a coil of insulated copper wire. 7. A current-carrying conductor, when placed in a magnetic field, experiences a force. If the direction of the field and that of the current are mutually perpendicular to each other, then the force acting on the conductor will be perpendicular to both and will be given by Fleming's left-hand rule. This is the basis of an electric motor. An electric motor is a device that converts electric energy into mechanical energy. Number 8. The phenomenon of electromagnetic induction is the production of induced current in a coil placed in a region where the magnetic field changes with time. The magnetic field may change due to a relative motion between the coil and a magnet placed near to the coil. If the coil is placed near to a current-carrying conductor, the magnetic field may change either due to a change in the current through the conductor or due to the relative motion between the coil and the conductor. The direction of the induced current is given by the Fleming's right-hand rule. 9. A generator converts mechanical energy into electrical energy. It works on the basis of electromagnetic induction. 10. In our houses, we receive AC electric power of 220 volts with a frequency of 50 Hz. One of the wires in this supply is with red insulation called live wire. The other one is of black insulation, which is a neutral wire. The potential difference between the two is 220 volts. The third is the earth wire that has green insulation, and this is connected to a metallic body deep inside the earth. It is used as a safety measure to ensure that any leakage of current to a metallic body does not give any severe shock to a user. 11. Fuse is the most important safety device used for protecting the circuits due to short-circuiting or overloading of the circuits. Coming to exercises. 1. Which of the following correctly describes the magnetic field near a long straight wire? A. The field consists of straight lines perpendicular to the wire. B. The field consists of straight lines parallel to the wire. C. The field consists of radial lines originating from the wire. Or D. The field consists of concentric circles centered on the wire. Question 2. The phenomenon of electromagnetic induction is A. The process of charging a body. B. The process of generating magnetic field due to a current passing through a coil. C. Producing induced current in a coil due to relative motion between a magnet and the coil. Or D. The process of rotating a coil of an electric motor. Question 3. The device used for producing electric current is called A. Generator, B. Galvanometer, C. Ammeter, or D. Motor. 4. The essential difference between an AC generator and a DC generator is that options are A. AC generator has an electromagnet while a DC generator has permanent magnet. B. DC generator will generate a higher voltage. C. AC generator will generate a higher voltage. Or D. AC generator has slip rings while the DC generator has a commutator. Question 5. At the time of short circuit, the current in the circuit, options are A. Reduces substantially, B. Does not change, C. Increases heavily, or D. Very continuously. Question 6. State whether the following statements are true or false. A. An electric motor converts mechanical energy into electrical energy. B. An electric generator works on the principle of electromagnetic induction. C. The field at the center of a long circular coil carrying current will be parallel straight lines, or D. A wire with a green insulation is usually the live wire of an electric supply. 7. List 2 methods of producing magnetic fields. 8. How does a solenoid behave like a magnet? Can you determine the north and south poles of a current-carrying solenoid with the help of a bar magnet? Explain. 9. When is the force experienced by a current-carrying conductor placed in a magnetic field largest? 10. Imagine that you are sitting in a chamber with your back to one wall. An electron beam moving horizontally from back wall towards the front wall is deflected by a strong magnetic field to your right side. What is the direction of the magnetic field? 11. Draw a label diagram of an electric motor. Explain its principle and working. What is the function of a split ring in an electric motor? 12. Name some devices in which electric motors are used. 13. A coil of insulated copper wire is connected to a galvanometer. What will happen if a bar magnet is, number 1, pushed into the coil, number 2, withdrawn from inside the coil, number 3, held stationary inside the coil? 14. Two circular coils A and B are placed close to each other. If the current in the coil A is changed, will some current be induced in the coil B? Give reason. 15. State the rule to determine the direction of 1. Magnetic field produced around a straight conductor carrying current. 2. Force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. 3. Current induced in a coil due to its rotation in a magnetic field. 16. Explain the underlying principle and working of an electric generator by drawing a label diagram. What is the function of brushes? 17. When does an electric short circuit occur? 18. What is the function of an earth wire? Why is it necessary to earth metallic appliances?